Hello, this is Basu from Wayne State University. The purpose of this video tutorial is to demonstrate a software tool that we've developed called Droplet Morphometry and Velocimetry, DMV for short. DMV uses image processing techniques to not only identify droplets and plugs in digital videos, but also to be able to track them over time. So during the course of the video, DMV can create a time history profile of each drop or plug, tracking about 20 different parameters, including the size, the shape, the deformation, the orientation, pixel statistics within the boundary, as well as the velocity and trajectory of the drop over time. So we believe that this type of quantitative data can be very useful to researchers in the droplet microfluidics community. And for that reason, we are making this tool available. More information about DMV can be found in our Lab on a Chip publication. And if you're interested in obtaining the software or would like to know more, please feel free to contact me at my email address abasu@eng.wayne.edu or visit our website at microfluidics.wayne.edu. Let's begin by opening the movie. So click here. We select our movie, which is a video of a flow focusing drop generator from Fluigen. So you can see the title of the movie here, the resolution here, the number of frames, the size of the movie, and also some information about the pixel depth and color. So just a word of note that in order for this video to be compatible with the DMV tool, which is based in MATLAB, we had to convert it to the AVI format. So fortunately, there's a nice open source software tool called AVI Demux, which is available at www.avidemux.org. And you can open up a video in that tool. You can set the output codec to XVID and then save the file as an AVI. And if you do that, it should be compatible with this software. Now that we've loaded the movie, you can see that by clicking on one of these arrows, you can advance the movie one frame at a time. If you click within this region, you can advance the movie 10 frames at a time. So as we'll see later, we may want to analyze only a section of the video instead of the whole thing. So let's click on this. We can drag this back to the beginning of the video. We can also select a region of interest. The best way to do that is to just click on the select button here, the left mouse button. Again, using the left mouse button, draw a box, and then double click with the left mouse button inside, and then your video becomes cropped during the analysis. Now, one of the reasons for doing this is because we might not be interested in analyzing the entire video. We might only be interested in analyzing a small region, a detection window, if you will. This also saves time because you're not analyzing as many pixels. But for the purposes of this video demonstration, let's click Reset to go back to the full frame. And then what we're going to do is select a region here. Okay, a region just in the middle of the video, which includes, excuse me for a second, it includes the flow focusing region, it includes the downstream channel, and it also includes this timestamp here. Now the reason we're doing this is to show how the DMV image processing steps can be used to filter out certain unwanted features in the image, like a timestamp or this junction region here. So at this point we have our video and we have a region of interest. Now we'll enter the frame rate and the length scale, which is used for velocity and size calculations. The frame rate is relatively straightforward. We know from beforehand that this video was shot at 5,000 frames per second, so we can put that there. For the length scale, there's a useful thing called the distance tool. So if you click on this, this brings up this line here, and we can drag the edges of that line to a region where we know what the dimension is. So for example, here we'll position this along, position this across the width of the channel. Now, say for example, if the channel is 100 microns wide, and this distance here gives you the length in terms of the number of pixels, then the length scale will basically be 100 divided by 134, or in other words, about 0.74 microns per pixel. And if you click enter here, then that distance tool will disappear, and at this point we've set up our entire video. So we have the length scale, frame rate, region of interest, and so on. The next step is to generate a background image. Now this is very important because DMV uses the background image to distinguish the moving droplets against a fixed background. So in most cases the ideal background image will simply be a picture of the empty channel without any droplets in it. But the caveat is that this picture must be taken with the same exposure, lighting, and resolution, basically the identical conditions as the movie itself. In some cases this is feasible, and if that's the case you can select the background image here. Just click this button and select the image and it will load it up. In many cases this is not feasible or convenient, so DMV has a way for you to auto-generate a background image, and so I'm just going to demonstrate a few ways to do that. So the first example we're going to do is using the averaging method. So let's put in one. We are going to average frames 1 through 100. Click this button here. So what's happening here is that over time at each pixel we are taking the average value of each pixel from frames 1 through 100. And as we go up in the number of frames that we average, you can see that the droplets start to basically disappear. So this is a simple longitudinal averaging technique that can be used to generate a background image. You can see that this is not perfect. You can see some darker edges here and here, which can sometimes cause issues with the DMV processing steps. In some cases, but not always. In fact, this will work fine as a background image. But we've found that this a technique called the statistical mode works even better. So let's go to mode here. Again, we're going to do frames 1 through 100 and click auto generate background image. So what the statistical mode does, it takes each pixel, it looks at frames 1 through 100, and it determines the most common intensity at that pixel. So the mode is actually able to generate a very high quality background image, you can see here, by exploiting the fact that at each pixel, the intensity of that pixel most of the time is going to be that of the background channel. The droplets are only moving over this thing momentarily. So most of the time, the intensity of that pixel will be that of the a background frame. So in addition to the mode and average, there's also the median, which gives you a result similar to somewhere between average and mode. There's also the min function, which will actually give you a very dark background channel. This is useful for the image inversion strategy, which is discussed in the lab on a chip paper, but is not the topic of this video tutorial. The max function will give you a lightened region where the droplets are flowing, and the average I mentioned earlier. So for the purposes of this video, we are going to stick with the mode function. So at this point we have a nice good quality background image of the empty channel. At this point it's worth mentioning that at any point during the process you can save your files. So as we'll see, we're going to have a number of settings that we have to enter into the software, and later on we're going to have a lot of data as well. So it's nice to have a way to save all your settings and data. So the way you do that is just by going to File, Save As. We can call our file Save1. It saves it in a MAT format, which is a binary format. Save the file. And just to demonstrate, if I were to change the background image here, for example, using the min function, if I change the region of interest and so on, I can restore that just by opening this save file again. Now let's move on to the main DMV image processing steps, which are used to identify the droplets in the video frame. The first step is background subtraction. Now in this step, the background image that we previously generated can be subtracted from the image frame. So let's see what happens when we do that. If we use the standard subtraction, this will give you an image, a grayscale image, where the drops and the moving features are highlighted, and the background or the non-moving features are basically removed from the image. So it's sort of a differential detection scheme. Now if you were to invert this image, this will create a white boundary around each one of the drops and moving objects. So this is what we're going to do, because the white boundary will actually be used to do the object identification. In addition to the standard background subtraction, there's also the absolute difference. Okay, let's take off the invert mode first. Go to absolute difference. Now this will basically take the difference between these two images and the absolute value of that. And this we found works in most general cases, even when you have light drops versus dark drops. It works in both of those cases. So we're going to stick with the absolute difference as a background subtraction method here. And you can see that we have a light boundary around each drop. The next step in the process is edge detection. Edge detection will take this grayscale image and convert it to a binary image. A binary image consists of just zeros or ones at each pixel. There are several methods we can use for edge detection, and all of these methods will basically identify the boundary of each one of these objects that we see here. The first method is called threshold edge detection, and this basically thresholds each one of the pixels. Anything that's larger than a certain threshold will be set to 1. Everything below that threshold will be set to 0. And this is the threshold parameter that you enter, and it's going to be a number between 0 and 1. So if we set this to say 0.01, for example, if we set it very low, then we'll see that we are going to pick up the objects, but we're also going to pick up a lot of extra noise. In fact, if we make this even lower, we'll see that we'll pick up a lot of noise. So by slowly increasing this value, we can get to a point where the objects that we're trying to detect are being picked up, but the objects that we are not trying to detect are disappearing. So let's say we set a parameter of 0.1 here. Now we can see there's a nice boundary around each one of these drops, and there's not too much extra noise. On the other hand, if we make this too high, if we make it 0.6 for example, then we won't be able to see anything. So this is a parameter that can be tuned depending on the how intense these boundaries are. So threshold detection is one method. We can also do the Sobel method. In the Sobel method, the way that the edges are detected is by computing a spatial gradient in intensity. So you can see how this region is dark and this region is light, so there's going to be an intensity gradient here. The Sobel and the Canny methods rely on this type of intensity gradient calculations. So again, finding the correct parameter between 0 and 1 is the same sort of thing. We can start off at a low value, say 0.001. We can see that we have a lot of noise here. We can increase it to 0.01. We can see that most of the noise starts to go away, and by the time we get to 0.02, 0.03, much of the noise has disappeared. If we set it too high, then we won't be able to see anything. So let's go back down to a value of 0.02, I think. We might be able to even increase it a little bit more to 0.025. Okay. Now also notice that the Sobel method actually creates two boundaries. One on the outer edge, where there's a gradient from transition from dark to light on the outside. There's also a transition from light to dark on the inside of the drop. So that's why you end up with two of these boundaries, but we can fill those in later. There's also the Canny method. The Canny method uses two thresholds, but we're only going to be entering one here. Again, the process is similar. You start off with a low value and you slowly increase it until you start to see some of the features. So we'll go to 0.1, 0.07, a little bit less than that. Okay. So the candy method works well when you have a lot of droplets which are packed closely together. In other situations it may not work as well. So during this process you can select whichever one seems to work the best for your particular video that you're analyzing. So let's go back to using the threshold method with a parameter of 0.1, since that seems to create a nice boundary around each one of the drops. Now that we've drawn a boundary around each one of these objects, we go on to the next step, a small object removal. Now, the purpose of this step is actually to reduce or eliminate small erroneous objects that may have appeared during step 2. For example, if we made this threshold very small, we'd have a lot of these erroneous objects, and one way to remove those is to use small object removal. Let's put this back to 0.1. So, for example, here what we could do is we can use a small object removal to get rid of these artifacts here which appear due to the timestamp. We put in a parameter called the minimum pixel size, and any object smaller than this in terms of the number of pixels it occupies will be removed. So for example, if we put 0 here, every object stays. If we put 1000, some of the small objects start to disappear. You can see that the timestamps disappeared. If we moved up to 10,000, for example, sorry, let's put this up one more, then all the objects would be removed. So again, this is a parameter which can be determined empirically. So since this object and this object, they're about the same size, we can't remove this artifact using the small object removal. We'll remove it later in the process. The other feature in the object removal step is that you can delete the border objects. So let's uncheck this. And if you uncheck this, you'll see that this drop, which is at the end of the image, appears. Now, if we try to do calculations on size and area on a drop that's only partially in the image frame, we're going to end up with errors. So this step allows you to select delete border objects, which will remove any object in contact with the border. And now we're left with our 2 drops here, which are fully in the image frame, and along with this other artifact. The next step is the morphological fill and close. And so the goal of this step between steps 3 and 4 is the close operation will actually fill in any object that has a continuous boundary around it. So for example, you see that these 2 drops here have a continuous white boundary around it because we've set it up, we've done the image processing steps to create that boundary. These boundaries are closed, so these droplets get filled in, and so now you have a filled object which will be used for the detection later on. Sometimes what you might have is an incomplete boundary, and to demonstrate that, let me change this parameter to 0.2 instead of 0.1. Now what you can see is that this drop here has a slightly open boundary here, and this drop has a larger discontinuity in the boundary. So the fill operation isn't working as we'd like. So the morphological close operation, what that will do is that allows you to select a certain brush radius in order to fill in some of these empty spaces. Now when we're talking about the close operation, imagine that you're taking an object, a pencil if you will, that has a radius, a tip radius equal to the number of pixels that you enter here. If you were to run that object along this white line, if that pixel radius is large enough, it can actually fill in the discontinuities here. To do that, the radius, the pixel radius must be larger than the size of the discontinuity in pixels. So let's try increasing this number and see what happens. If we go up to 10, we can see that this region got filled in here. If we increase it to 20, that should be enough to actually fill in this discontinuity here. And you can see that the drop is now filled in. This one still is not, so we actually have to increase this number even more to 50. 50 didn't do it. Let's go up to 60. Okay, 60 filled this object in. So that's because the distance between this point and this point, the discontinuity, is about 60 pixels. So you notice that this drop is still a circular object, whereas this one, since you don't have the circular boundary around it, it ends up being sort of like a pie-shaped object. So you can make this brush radius as large as you want. However, if you start making it too large, you're going to start distorting the drops even further. And if you make them very, very large, let's say 500, then you can actually start to form a bridge between the drops and the walls or each other. Let's change this back to 200. You can see some of the bridge forming here. At 100, that bridge starts to kind of go away. Okay, so let's set the brush radius to what it was originally. Let's set this back to 3, and let's change this threshold back to 0.1 to what it was before. So again, the key thing in this step is to make sure that each one of the drops that you're trying to detect is filled in completely. This is something that we can filter out at a later step, so it doesn't matter if this is filled in or not. The next step is a morphological erode. Now I just want to point out that this step is actually not discussed in the lab on a chip paper, and most of the time we don't use it. But I thought I'd mention it anyways in case that it might be useful for a subset of videos. If you have drops that are packed closely together, sometimes you may end up forming a bridge between the two drops in this fill and close step. So what you can do is you can use this erode step to actually remove that bridge between the two objects. Morphological erode is kind of like the opposite of the morphological close. So imagine that you have an object, so we can select a disk, for example, and the radius of that disk, if we set it to say 10 pixels, what it's going to do is going to erode every object that it finds by 10 pixels. Okay, let's go back to 1. So you can see if you erode the edges of this by 10 pixels, you're going to end up with a smaller disk. Okay, but the interesting thing is, if you look over here, this object here is actually, it's less than 10 microns wide. So if we erode this line from both sides using a 10 micron disk, it's actually going to eliminate it completely. So this is one way that you can get rid of some of these erroneous line objects while keeping your objects which are more like polygons. But we're not using the morphological erode here, so let's just turn this step off. And again, we're still left with our two drops and this extra object here. The sixth DMV processing step is shape discrimination. And the purpose of this step is to, again, remove erroneous objects which do not meet a certain user-defined circle metric. So we have this object here which is not circular. We'd like to remove that artifact, and we'd like to keep these circular objects. So this is all controlled by a circle detection threshold, which is a number between 0 and 1. If we set this number very low, this means all objects will be recognized and identified. As we start increasing this number to say 0.5, this object disappears. And if we make this number too high, say 0.99, then none of the circles will be detected either, because that circle metric is very, very high. So let's set this back down to 0.5 so that we can detect our drops, but not this this artifact here, which is non-circular. So the third step gives you a way to remove erroneous objects by removing them by a size threshold, so basically to remove small objects. And then this last step gives you a way to remove non-circular objects. So using a combination of these two methods and the edge detection, in most cases it is possible to filter out the moving drops from the background. And this is the DMV results window. You should be able to see, if you've done these steps properly, you should be able to see that only the drops in your image are circumscribed by this line here, and that's this red dot in the middle shows the centroid of the object. Now that we've completed the 6 image processing steps and we've identified the drops in one of the frames, we can move on to the movie analysis. So I'm just going to talk about each one of these settings right now. The start frame and the end frame tells us which frames of the movie you'd like to analyze. So for the time being, we are going to analyze frames 2 through 3. So you can see each one of these 2 drops in the middle moves slightly between the 2 frames. So let's set this to 2 and 3 just for the sake of demonstration, so you can see the effect of the frame correlation settings. The frame interval is set to 1. This tells you how many frames you want to skip. So a lot of times when you're dealing with high-speed videos, let's say at 5,000 frames per second, the frame rate was too high, so the droplets are hardly moving between 2 frames. If this is the case, the analysis can actually take a very long time. So what you could do is set the frame interval to 10, and the software will then only analyze every 10th frame, and this way you can speed up your analysis. For this demonstration, of course, a frame interval of 1 is fine. These 2 are the frame correlation settings. So the 6 settings that we showed here are used to identify the drops, and then these 2 frame correlation settings are used to link drops between subsequent frames. So again, we see here that this drop is, in frame 2 it's here, in frame 3 it's just moved over slightly. So how can we link the 2 together? The software does that by using these 2 user-defined settings. The first setting is the distance match factor. And this is telling us what is the maximum distance the drop can move between 2 subsequent frames. And this number is normalized in terms of the drop diameter. So this is telling us that the drop can move 1.2 times the drop diameter per frame. That's the maximum distance it can move. If it exceeds this distance, then the linking will not occur. The second one is the area match factor. This tells us how much can the drop size change between 2 subsequent frames. So in this example, of course, we don't expect the drop size to change much at all. We've just put out a conservative number here, 0.2. Again, this is a percentage, so this is telling us that the maximum change of size you can have between one frame and the next is 20%. So if either of these 2 criteria are not met, then the linking will not occur. So let me show you an example here. If we just start the analysis, we will analyze frames 2 through 3. Okay, you see the analysis occurred because you can see these 2 velocity arrows appear. To measure a velocity, of course, you have to have 2 position measurements, so you can see that the droplets were in fact properly linked. The other way you can see it is by looking at some of this data here. This tells you the current frame number which is being analyzed. We're on frame 3 at this point. This is the number of droplets in the current frame, so there are 2 droplets found in frame 3. This shows the number of matches from the previous frame. So this is telling us that 2 droplets were matched to the previous frame. So both droplets that were found in frame 3 were had matches in the previous frame. And the number of new drops that were found in frame 3 is 0. So no new drops were found. So this means that both droplets were properly linked to the previous frame. And the total number of droplets is equal to 2. This is keeping track of the total droplets that you found in the entire movie analysis. So it's not really relevant here, but you'll see that this number will accumulate the more frames that we analyze in a movie. So just to show you the effect of these settings, if we make this setting very, very small, and we make this one very strict as well, we rerun the analysis, we'll see that not only do we not have arrows here, but the colors have changed. The fact that we have different colors here means that the software has identified the drops as new drops. You can also see this here. We can see that there were 2 drops found in frame 3, and both of them were identified as new drops rather than being matched to the previous frame. And the total number of drops is equal to 4 because we had 2 in the previous frame and then 2 in this frame. So this shows you that they were not properly matched together. So let's change this back to 1.2, and we can change this back to 0.2, the settings at which they were at. I'd like to show you a few more features here. If you want to display the statistics, you can check this box, and this will give you the metric, the circle metric, how circular the object is, the centroid, the size, the area, and the mean pixel intensity inside the object, inside the drop. Okay, so you can enable this or disable this by clicking this button here. You can also change the size of the arrow. If you want to make the arrows larger, then you can see that you get larger arrows here. So let's move this back down to 3. We can keep the stats on just for display purposes. The final thing I'd like to show is if we're analyzing a long movie, you can actually stop the analysis and restart it. So let's set this to 30. And we can start the analysis here. When you click the start button, then you'll see now you can again click the same button to stop the analysis. So we can click stop here. Okay. And you can see here that some of the data is being filled in. So let's change this now to analyze the entire movie, frames 2 through 196. Okay. And then let's go ahead and start the analysis. Okay, we're just going to wait a little bit for this analysis to complete. While it's doing that, you can see what's happening here. This is showing each frame of the video, each of the image processing steps, so you can observe what is happening if you need to change any of the settings in one of these steps. Over on the DMV results window, you can see the arrows showing. So these arrows are showing that the droplets are being linked properly to the previous frames. You can see here that the current frame number is going up. This slider is also going up as we increase in the number of movie frames. This is showing us that depending on which frame we're talking about, there's either 2 or 3 droplets being identified per frame. And in general, they're all being matched to drops in the previous frame. So the linking is happening properly. There are 0 new drops in the current frame most of the time. And then when a new drop emerges from the junction, you can see that this number changes to 1. Okay. And this is keeping track of the total number of drops that were found in the video. On the right side here, you can see that we are accumulating all of the data. Okay. If you want to disable the plots or disable the images, you can click on either one of these buttons here. I'm not going to do that right now since it's running. But what that will do is that will actually make the analysis run much faster. Because it turns out that a lot of the CPU time is taken up by actually generating these images. If you've done the settings properly, then you don't need to actually view each of these movies as it's happening. You can disable the DMV images, and if you want, you can disable the plots as well. And it won't plot frame by frame. It'll just show you these plots once the analysis has been completed. The final option here is that if you want to generate a movie, you can click this option here. Now, in order to generate a movie, you do have to enable showing the DMV images. Let me just disable this for a second so you can see that by clicking this button, this will basically blank out this entire window here. And by clicking this DMV plots, you can basically remove that. And if you do the analysis without these options enabled, like let's try this again right now, you'll see that the analysis actually works much faster. In most cases, we can observe that the analysis runs like 2 to 3 times faster if you do not have the images enabled. That being said, that once the analysis has been complete, the data will still show up. So if we just wait a minute here for the end of the movie to come up, you'll see that once we get to frame 196, all this data will still be plotted in the end. So this can save you some time if you already know what settings you have to set. And then the final thing in this window is the Generate DMV Movie option. So if we wanted to generate a movie showing the moving drops with the arrows so that you can later confirm whether the analysis was done properly or not, you can enable this option. So let's click this, and let's also click the Generate DMV Movie option. Okay, and let's keep this short. We only want to do a small portion just in the interest of time here. Let's set this to 20. So we'll only analyze frames 2 through 20. And when we click Start Analysis here, it will ask us for where we want to save the movie that we're generating. So let's call this Fluigent-DMV, and it'll save it as an AVI file. So we click Save. The analysis begins, same as before. The only thing different that's happening this time is that it's also saving a video simultaneously. So if we were to now look in the desktop in the example here, we can click on this movie and it will show this movie that we just generated. So this is good for illustrative purposes. It's also good that if you want to let the simulation run overnight, you can let this movie generate also, and when you come back in the morning, you can look through the movie to make sure that the linking was done properly. It just gives you another way to do some error correction. Okay, now we can get to the quantitative plots for the data analysis. You can see that I've actually run the entire analysis frames 2 through 196 again so that we could regenerate the data. And again, you can save, once you finish running an analysis, you can save it so that you don't have to rerun the analysis again. So looking at this area, we have 4 different plots here. 3 of these are scatter plots, so you can plot any one parameter against another, and you can select those here, and you can do some filtering in this last box here. The last graph here is a histogram, where you can plot statistical data. So let's look at this one, for example. What we have here is a plot of Y position versus X position for each drop that is found. And so you can see that these dots are colored by drop ID, so all the red drops are of a certain drop ID, and so on. There's only about 8 colors or so, so once the DMV software, once you get to drop 9, it recycles back to the first color. So obviously there's a little bit of overlap here. In this plot of Y position versus X position, you can get a trajectory of the drops, and in this case all the drops follow the same trajectory. You can see that the Y position changes slightly. This is probably due to the drop break off, and then it follows this straight line here. An interesting plot we could make here is just to show the shape eccentricity versus the X position. So X position is the distance along here, and the shape eccentricity is a measure of how deformed the drop is. So it's a number between 0 and 1. Closer to 0 means it's more spherical or more circular. Closer to 1 means it's more deformed. So you can see that the eccentricity goes up to 0.6. This is at the moment of drop breakoff, and then it quickly goes down to 0.2, which is a very circular shape, and then it stays in that deformation during the rest of the time it's in the channel. So this transition from a deformed shape into a circular drop happens over the course of around 100 microns or so. Besides this, there are several different parameters. Droplet ID is a unique identifier for each droplet. Frame number is, the current frame number. Time is self-explanatory. The X and Y position are used for trajectory measurements. X and Y velocity for velocity measurements. Velocity magnitude is the total velocity, including the X and Y components. The area, this is the area in microns squared. The major axis length, the minor axis length, also in microns. Equivalent diameter, the orientation. The orientation of the drop only applies if you have non-spherical plugs. So if you have a plug that's more elliptical, it's going to have a certain orientation to it, and this gives you the orientation in terms of the number of degrees. Shape eccentricity, I mentioned, is a metric that describes shape deformation. The circle metric is what we showed earlier. It's a parameter that's used to detect circular versus non-circular objects. So these two are actually quite similar. The only difference is for this one, the circle metric, the closer this number is to 1, the more circular the object is. Whereas here, the higher the number is, the more deformed the object is. Mean pixel intensity is the, you can click that here. This shows you what the average pixel intensity within this boundary is. Okay, this is also what's shown here. And if we plot this, we can kind of see that the mean pixel intensity actually increases as we go towards the right side of the channel, probably due to some non-uniform lighting between these two sides. So it can actually pick up relatively small changes in the pixel intensity. So mean pixel intensity is the average pixel intensity within the boundary. This is the maximum pixel intensity within the boundary. This is the minimum. There's also the standard deviation. So if you want to see how much variation in pixel intensity there is within the drop, which is useful for looking at things like mixing operations, you can do that. And then finally, there's the distance to the nearest neighbor. This actually plots the distance between each drop to its nearest neighbor. Okay, and this actually applies, it's more relevant to when you have packed emulsions and you want to see how closely those emulsions are packed. Let's put this back to the shape eccentricity plot here versus X position. So in this one, we've selected all the data. I'll show you what this means in a second. The second plot we've made here is the velocity magnitude versus the X position. And again, we've plotted all the data. So the interesting thing that you notice here is that this actually reveals some flow perturbations which would be very difficult to reveal by manual analysis. And it's very difficult to actually see them visually. So what we've done here is we've plotted the magnitude of each drop versus X position, and we've included all drops at all data points. So what you can see here is that there's an oscillation. When the drop breaks off, the velocity is larger. It's close to 1.8 times 10 to the third micrometers per second. Actually, it might be 10 to the fourth there. So the velocity drops off as you go to 500 microns, and then it increases again, and it falls, and it increases and it falls. And what you notice is that all the droplets in the series, all 32 of them, follow the same sort of velocity pattern. So the reason why this happens is because there's a periodic breakoff, and when that breakoff occurs, it creates a slight flow perturbation in the channel, and that perturbation is periodic, so that's why you see this type of periodic pattern. You'd also see this type of pattern with respect to time, but it's a little bit more difficult to see. It's easier to see it in terms of the position here. Okay, moving on to the next graph. A very useful graph to do is the drop ID versus the frame number, or equivalently the drop ID versus time. Drop ID is a unique identifier for each drop. It's incremented each time a new drop is found. So if we were to plot drop ID versus time, the time is calculated by using this frame rate parameter that we put in earlier. We get a plot that looks like this. Now, the other point I want to make here is that we've selected 1 point per drop. If we select all data, you're going to see horizontal lines representing the times during which each drop was found in the movie. Just to simplify this, we can choose to only plot 1 point per drop. So we select this to say we only want a single point per drop, and what we're going to do is plot the first time point that the drop was found. Then we'll get something single like this. We can also plot the median value, we can plot the maximum or minimum value, and the first and last value. But in this case, we're only plotting the first value. So you see this nice straight line here, and what that represents is that we have uniform drop generation over time. The slope of this line is the frequency of drop generation, because this number is being incremented by 1 every time a new drop appears, and on the x-axis we have time. So we have drop number versus time. So if you just take the slope of this plot, you will basically get the drop generation frequency, which is about 800 drops per second in this case. The final plot here is a histogram. So what we've done is we've plotted the drop area, okay, the drop area in terms of the micron squared, and we've done a histogram of that. So when you're doing histograms, it's generally good practice to just do 1 point per drop. Obviously, you don't want to have multiple time points for each, multiple pieces of data, multiple counts for each drop that's found. You only want a single point per drop. So we're choosing the median area that was found. And there were a total population of 32 drops. So this is what the histogram looks like. You can see that the area is centered mainly between 7950 and 8000 microns squared. We can change the number of bins if we'd like for a higher resolution or a lower resolution. I think for this particular, the number of population that we have right now, which is relatively small, 20 bins is fine. We can plot any parameter. We can plot a histogram of the diameter, for example. This tells you the different diameters were at approximately 100 microns. So this is very good for determining the monodispersity of drop populations. That's what we generally use it for most often. If you do a histogram of the nearest neighbor spacing, that's good for investigating packed emulsions and seeing just how packed it is. If the looser the packing, then obviously the distance to the nearest neighbor will get skewed in one direction. In a perfectly packed emulsion, it'll be relatively tight. So let's go back to the diameter here. And so we've generated these 4 plots of data that's useful for quantitative analysis of this flow focusing drop generator. Okay, so now that we have all the data, I'm going to show you how to save and export the data for use in a report or manuscript or what have you. The first thing you can do is you can take these 4 plots that you've generated here and even these images here and generate a PDF out of it. To do that, you just click on this button called Export Plots and choose the directory that you want to save those PDFs in, and you'll see these 3 windows pop up. Let me drag them over here so you can see. Figure 1 contains all the 4 plots that you selected, including the labels and whatnot. The second plot contains the original image frame, the background image frame, and then the analyze frame, just for illustrative purposes. And also for illustrative purposes, the figure 3 shows the various image processing steps that were used to obtain this analyzed image. So if we close these windows here, and if we look at our current working directory, we'll see that there are 3 PDF files in there which have the same data. You can see the image files here. Okay, and the PDFs were made so that the width of each of these figures is somewhere between 2.5 inches, something like this. So it's made to be put in the column of a journal manuscript, and that's how we did in our lab on a chip paper, in fact. So these PDFs can actually be imported directly into Word or whatever vector graphics program that you may be using. Since it is in vector format, if you zoom in here, you'll be able to see you don't get the pixelation that you would if in a bitmap image. So it's a nice way to be able to export your data. Now in some cases you may not just want scatter plots of the four things here or a histogram. You might want to have the quantitative data yourself so that you can generate your own plots in whatever format you choose. So to do that, all the quantitative data in DMV can be exported to a text file in a report format. So the way we can do that is I'll show you by example. Let's say, for example, we are interested in three things. Let's say we're interested in the time. So we can select time as one of the fields. And we are interested in the velocity magnitude, so we can control click here. Control click is toggling, by the way. And we're also interested in the equivalent diameter. So by going through this list, by using control click, we can select multiple parameters. So we selected 3 of them here. And when we do that, then we just click export. Select a file name. We'll call it data.txt. And then click save. This data file is saved in a tab delimited format. So if we right click on this and open it with Excel, we'll be able to see this report. Now there's quite a bit of data on here, so let's go through each one of these parts specifically. It starts with a droplet summary report, which basically says the number of droplets that were found in the number of frames and in the video time. So 32 droplets in 194 frames, 0.038 seconds. What follows this is a statistical summary of each drop, and then all the details on each drop at each time point. So this is more like the raw data. This is kind of a statistical summary. So let's talk more in detail about the statistical summary. So I mentioned earlier that you can see from the video that each drop is actually identified at multiple time points as it traverses from one end of the video to the next. For example, droplet 1 was identified at 12 different time points. That's where this n equals 12 comes in. So that's kind of like the population for droplet 1, all the time points for droplet 1. So for this population of 12 time points, each row will give you a statistical summary based on that population. So we chose 3 parameters of time, the velocity, and the equivalent diameter of the drop. So this is telling us that droplet 1, these are all the statistical analyses of the time. So the first time the drop was identified was 0.4 seconds. The last time it was identified is 0.0026 seconds. So the minimum, the maximum, the range, the median, the mean, and the standard deviation coefficient of variation. So for something like time, calculating the mean and median and standard deviation, it's not really that relevant. So you really have to choose which parameters are relevant, which ones you'd like to include for your analysis. For velocity magnitude, you'll notice that the first velocity measurement is always NaN because you need at least 2 time points to do a velocity measurement. At the last time point, when the droplet exited the channel, the velocity was the value that you see here. This is the minimum velocity, maximum velocity, the range, the median, the mean velocity, and the standard deviation of the velocity and the coefficient of variation. The coefficient of variation is just the mean value divided by the standard deviation divided by the mean value. If we look at the equivalent diameter, again we have the same parameters. Minimum and the maximum values, the first and last values, the range, the median, the mean. So this is telling us that droplet 1, of all the 12 time points it was found, the median diameter was 100.8 microns, and the coefficient of variation was 0.23%. Okay, so for each row we get a statistical summary of each drop, and so this will go from droplet 1 to droplet number 32. This last line here gives a statistical summary of the entire population. So, for example, if we wanted to get the monodispersity of the entire population, like the statistics on drop diameter, this column is telling us the mean, and this one's telling us the coefficient of variation. So each one of these entries is for each drop, but if we want to look at the entire population, we can see that the mean value for the entire population was 100.7, and the coefficient of variation for the entire population of drops in the drop diameter was 0.12%. This is quite small in this case. So this is nice for accruing statistics over the entire population. Now, in many cases, you want details of each droplet at the granularity of a single droplet. Now, in that case, you'd want to look at the details section down here. So this is showing a table where each droplet has however many time points it was cited. So there's 12 time points for droplet 1. These are each of the times that the droplet was identified. These are each of the velocities at each one of the time points. And this is the diameter measured at each one of the time points. So this is sort of like the raw data that you can use to do your own statistical analysis of the drop population. And this obviously will go all the way up to drop number 32. Okay, so this Excel report gives all the data that you can use to generate your own reports or your own graphs and what have you. This is all the data pretty much that the DMV software can measure. So you can include all 20 different parameters if you'd like, or include whichever ones you feel are necessary for and relevant to your video and the type of information that you are trying to obtain. Okay, so let's close this here. Okay, so this brings us to the end of the tutorial on DMV. We've gone through how to load a movie and how to set a region of interest, the length scale, and the frame rate. We went through the 6 processing steps and the parameters involved at each step and how to optimize each one. Then we went through the movie analysis settings, including the 2 frame correlation settings that allows the software to link droplets in subsequent frames. We looked at how to qualitatively and quantitatively look at the results to make sure that the image processing settings are correct. And then we talked about how to generate 2-dimensional scatter plots in histograms for analysis, and these plots can be exported in a PDF format. And then finally, if you want a raw quantitative data that was generated by the DMV analysis, you can export them into a text file, a tab delimited text file that you can open up in Excel. So I hope that you found this tutorial on DMV useful and that you find the software equally useful. Any feedback on either can be sent to my email address, abasu@eng.wayne.edu, and our website, microfluidics.wayne.edu, will be updated as needed with documentation related to DMV and potentially any software updates or bugs that may come about. Thank you for your attention, and again, I hope you find this software to be useful in your work.